It is your lucky day because this video is a derivation of the kinetic theory of gases. Now before you fast forward or just skip this video altogether, give it a little chance. This is probably the coolest derivation we do all year in this class. It incorporates all kinds of different principles, forces and velocities and momentums and all of these things. And in addition, this was kind of the first time ever in all of science that we were able to link a macroscopic property like temperature that we can easily measure with what is going on the microscopic level. We can explain temperature with the motion of particles, which was a pretty amazing thing. It was James Clerk Maxwell, who is one of the best scientists of all time. He helped unify all of the theories regarding electricity and magnetism. So hang with me if you can. So let's get started here. The first thing we need to do is look at the ideal gas law real quickly, which we have been using as PV equals little n times R times T. This is doing it in terms of moles and the ideal gas constant, but we can redefine things because you can get the number of moles by doing the number of particles, which we tend to designate with a capital N, divided by Avogadro's number, which we designate with N sub A. So that is a number of moles times R times T. And then if we combine the ideal gas constant divided by Avogadro's number, we redefine a new constant, because these are both constants. This one here is known as Boltzmann's constant, and we don't really need the value at this point, but I'll put it up here just for fun. 1.38 times 10 to the negative 23rd joules per Kelvin, and this allows us to rewrite the ideal gas law in terms of the particle number instead of the mole number. So we got capital N times Boltzmann's constant times T, and we're going to use this again later, as well as you'll see this in some of your calculations. Alright, now in order to derive the kinetic theory of gases, again relating temperature to the motion of particles, first we're going to think about a box full of gas, which is a common thing in thermodynamics, lots of boxes of gas examples. And if we think about this, the particles in this box, they're going to be bouncing around any which way, a bunch of random motion. And if we think about a single particle bouncing around and making a collision with this wall over here, say this particle here is headed this way. Well, I want to kind of simplify my analysis, so I'm just going to take the x component, because velocity is a vector. So I'm going to take the x component of this velocity here, and just imagine the horizontal motion of this particle. Man, I don't know why it keeps erasing my lines here. Alright, so horizontally, when this particle collides with this wall over here, and I'm going to say it's a box of length L on all sides, okay? When it collides with that wall, it's going to bounce off. And when it bounces off, it's going to have a certain change in momentum. That change in momentum, if the velocity in the x direction was vx, it's going to bounce off, and now it's going to be negative vx. So the change in momentum is going to be 2 times m times vx, because you remember m delta v was our change in momentum. Our delta v is 2 times vx in this case. Alright, then we're also concerned with how often it's colliding with that wall, and we can get at the time by doing delta x equals vt, in this case vx, and that delta x is going to be the length of the box, but I want to know the time between collisions, so that's the time to go there and back. You know, if it just left the wall, it has to go all the way over here and then back. So delta x is 2L, and we've got vxt, so the time between collisions is going to be 2L over vx. Okay, I'm going to kind of circle these things here because we're going to use them later on. Now, if I'm interested in what happens to the wall when this particle collides with it, well, there's a force exerted on that wall, and force, we can use Newton's second law, equals ma, and we can define the acceleration as the change in velocity over time. And m delta v in the numerator here is the same thing as change in momentum. See, we're putting together all kinds of things that we've learned since last semester. over t. Well, I've got expressions for both of those things. So this is going to be 2m vx over 2l divided by vx, and that vx will come up top, and we can cancel out our 2's, so we end up with m vx squared all over l. Okay, now this is the force on that wall due to one single particle. But we have a box full of gas, so there's a whole bunch of particles. So what we need to do there is we just need to sum up the forces from all of the particles. So I'm going to have, if I assume it's a uniform gas, all helium or oxygen or hydrogen or whatever, then they're all going to have the same mass. The box is the same length L, and I just need to add up the velocities of each of my particles squared. Okay, Vx1 squared, Vx2 squared, plus Vx to the n squared. I guess there were supposed to be dots in there, right? Okay, so I have a factor for each of the particles. Basically, you have m over L times V squared for each particle, and we factored out the m over L because that's consistent between all of them. Now we can simplify this expression a little bit by saying, well, rather than finding the actual velocity of each particle and adding them all up, if I just know the average velocity of the particles, I can take that average velocity, we're going to designate that with a bar, and it's squared, and I multiply that by the number of particles. That's going to give me the same thing, because my average velocity squared is just each of these velocities Vx to the n squared divided by the number of particles, right? So I multiply that over here, and we'll get this expression here. We're going to take this over to the next page because we're running out of room here. So if we start with this expression that F equals, let me make sure I get this right, m over L times the number of particles times Vx squared averaged. Okay, so we'll start here. Now, I want to kind of generalize this to the velocity of the particles in any direction, not just in the x direction. And if we have random motion, well, actually, let me back up. The total velocity of the particle, velocity is a vector, so we can use Pythagorean theorem, a squared plus b squared equals c squared. But in 3 dimensions, we have the x component squared plus the y component squared plus the z component squared. These are all averages. Gives us our total average velocity. And back to what I was saying, if it's random motion, then Vx and Vy and Vz are going to be equal. So this reduces down to 3 times Vx squared, since these guys are all equal. And so then we can substitute in here, and we can say m over L times n, and then divide the 3 across, plug in for Vx squared. So we're going to have V squared average over 3. So now we're relating the force to the average speed of the particles, and we're starting to get somewhere. Now usually it's harder to measure the force against a wall, but it's easier to measure the pressure in a gas. So if we say the definition of pressure is force per unit area, so we take this expression for force and add an area in the denominator, and so we're going to have m n V squared average over 3L times the area. And the length of the box times the area of one of the sides is just the volume of the box. So we got mn V squared average over 3. I'm going to go ahead and write volume out so we don't confuse that with the velocity that we had before. And then we can multiply that volume up here with the P. I'll go ahead and write a PV because we know pressure and volume go together like that. mn V average squared all over 3. And what I'm going to do now is I'm going to multiply by 2 over 2. And if I combine this 2 in the denominator with this m and this v squared, I'm going to leave a 2 up in the numerator. and an n out here, and then all the rest of that stuff is going to combine to be 1/2 mv squared, which hopefully rings a bell, right? This is our kinetic energy, so we can say that PV is equal to 2/3. Actually, I'm going to put the n over here as well. PV over n equals 2/3 of our kinetic energy. Now this was average velocity, so this is our average kinetic energy. And we're almost done, so just stick with me for a little bit longer. We had that expression that I started with, that PV equals nkt. So PV over n is just equal to kT. So I can put a kT over here, where that's Boltzmann's constant times the temperature, equals 2/3 times the average kinetic energy, and then I just put the 2/3 on the other side. So I get the average kinetic energy of the particles is 3/2 times k, and all this stuff is constant. So basically I have the kinetic energy related directly to the temperature. Hooray! Yay for physics! We related a macroscopic property, temperature, with the microscopic average kinetic energy of all of these particles bouncing around. Pretty amazing. Now if we actually back up, well, let's go from right here and plug in 1/2 m average velocity squared equals 3/2 kT, just plugging in our expression for kinetic energy. We can get one more equation that's going to be useful, where we're going to solve this guy for the velocity. So we can know the average speed of the particles of a gas just by knowing the temperature. So 2's go away, divide the m over, and so we're going to have v squared average equals 3 kT over m. And then if we square root the whole thing, this quantity here is often called the RMS speed. Stands for root mean squared. So it's just a different way of taking an average, because if you just take the average of a bunch of random particles in different directions, you'll have some with positive velocities in the x direction and some with negative, and that'll average out to 0. But if you take all those velocities and square them, and then take the average, and then take the square root, then all the negatives go away, and you get this other quantity known as the RMS velocity. Okay, so here's our other expression, and we're going to consider this the average speed of the particles. All we need to know is the temperature and the mass of an individual particle. So this is one single particle. And there you have it, some beautiful symmetry between the macroscopic and the microscopic world, relating temperature to motion of particles. Thank you very much.